Hi everyone, we're Team A for the W, and today we're presenting SignEcho, a real-time ASL recognition and speech assistant. You may remember this viral video from MIT students demonstrating gloves translating sign language into speech. When beginning to brainstorm ideas, this video was a major inspiration for us. It showed how powerful assistive technology could be, but it also highlighted barriers. The gloves were specialized hardware, expensive, and not accessible to everyone. Thanks to advances in computer vision and machine learning, we could achieve a similar goal using only a webcam, removing the need for wearable devices and making the solution far more accessible. Despite technological process, communication barriers still exist today. Deaf and hard-hearing individuals face challenges in everyday interactions, ordering food, asking for help, or communicating in emergencies. Interpreters aren't always available, especially in spontaneous or rural situations. Existing solutions can be expensive, slow, or require specialized hardware, and most real-time accessibility tools are limited, making fluid communication difficult. SignEcho translates ASL into speech in real time using only a webcam. When a user signs, the system recognizes the sign, displays the translated text instantly, and speaks the results out loud. It runs live with no delays and adapts its speech tone based on facial emotions to better reflect how the message is intended. First, we use media pipe hands to detect and track 42 landmarks, 21 per hand, capturing finger joint positions, orientation, and depth. We convert these landmarks into geometric features such as relative distances and joint angles, which makes the system robust to lighting, background, and camera variation. To capture motion, we use sliding window buffering to build short temporal segments. This preserves gesture dynamics while maintaining low latency. These spatio-temporal features feed into the random forest classifier trained on 252 dimensional temporal feature vectors. We perform probability-based inference and sequence-based recognition to improve robustness during continuous signing. In parallel, we detect facial landmarks to classify the user's emotional state, such as happy, neutral, or surprised, and use the signal to control voice tone rather than to influence sign classification. Finally, we ensure stability using majority vote, temporal smoothing, and confidence threshold filtering to prevent flickering and suppress uncertain predictions. The recognized sign and emotional contexts are then fused to drive emotional-based text-to-speech output. Here's our demo.
Hello. My name is Jay. I develop program in OSU.
In addition to recognizing signs, the system analyzes facial expressions.
Hello.
I develop program in
OS.
you.
We started off with static alphabet recognition as a proof of concept. We then progressed to dynamic, real-time recognition, allowing continuous gestures and more natural signing. Some major challenges include flickering predictions between transitions, confusion between similar handshakes, lighting and background variability, and limited training samples. To improve usability, we added emotion-based voice tones. To evaluate performance, we used a confusion matrix to analyze classification accuracy across all signs. Most predictions fall along the diagonal, indicating strong classification performance. Our random forest model was trained on 1,819 samples and tested on 364 samples, achieving 94.8% accuracy. This demonstrates reliable recognition performance for real-time use. SignEcho improves accessibility and inclusion by enabling real-time communication between deaf and hearing individuals. It is affordable, scalable, and requires only a standard webcam. Next steps include expanding training data for better robustness, support full ASL sentences instead of individual signs, and build a cleaner, user-friendly interface. Our long-term vision is seamless, natural communication without barriers. We trained our system using the WL ASL dataset, additional ASL datasets from Kaggle, and custom videos re-recorded. We built the system using MediaPipe, OpenCV, and scikit-learn, and used 11 labs for speech synthesis.